I'd like you to welcome Professor Omar Hegazy and Professor Thierry Coosemans from the MOBI Research Centre, who will be talking, as you may have already guessed, about the powertrain design and modelling for light and heavy-duty vehicles. First, I'd like you to welcome to the stage Professor Thierry Coosemans. Thank you.
Hello. Good afternoon. Hello. Good afternoon, everybody. So I'm Thierry Coosemans from the University of Brussels. I'm working for the MOBI Research Centre, which has a focus on electric mobility. Now, Omar will give you a lot of information about how we design powertrains and power electronics, but I will give you a little bit of the context in which we work, mainly electromobility. So, how does this work? Yep. So, more precisely, what are the challenges for electromobility? We know that climate is an issue, global warming is an issue. 20% of the greenhouse gases are exhausted by the transport sector. And moreover, here you see a sunny morning in Beijing, China. Most of the NOx and a big chunk of the particulate matter is also emitted by the transport sector. Thirdly, Europe pays 1 billion a day for oil imports. So it's a huge amount of money that leaves the European Union per day. We all know that electromobility can be part of the problem for this, but somehow market share is only low at this moment. It's 1.5% in Europe, because there are still some issues, there are still some hurdles to be taken. The classical ones that are commonly known is high purchase cost for the moment, still limited driving range, and of course the limited availability of charging infrastructure. Now, with in relation to driving range, the specific energy, the amount of energy that you can store in a battery in the watt-hours per kilogram is a key parameter. Now, this has been a lot of progress the last 20, 30 years. Here you see one of the first generation commercial electric vehicles which we actually deployed at our university in Brussels with lead-acid batteries. Still a very low energy density of 30 to 35 watt-hours per kilogram. But then later, in the 90s, the first mass-produced vehicles came on the market with nickel metal hydride batteries, already doubling the capacity. Then we all know the later generations with the Nissan Leaf and so on, based on lithium batteries. There again, capacity doubled. And now towards 2020, we probably will see something like 400 to 600 watt-hour per kilogram on cell level. That will be in the next generation cars. And we see post-lithium 2030, what will happen then? We might even go further. So the range is still a little bit of an issue, or at least range at an affordable price is still an issue, but it's going to vanish in the coming years. As you can see here, actually, the evolution of the battery price the last 5 to 6 years decreased from $1,000 per kilowatt hour to 200 and a little bit nowadays. And it's foreseen that by 2020, probably the cost of a battery pack will be about €100 per kilowatt hour. So it's going really down. And you can see this in the increase of sales of electric vehicles, that it's still a slow market share, but the climbing is steep. So they're gaining market share. Moreover, what you can see is that, okay, the last generation a few years ago were basically in this part of the market with a limited range, like 120, 150 kilometers, and at an affordable price of 30 to 40,000 euro. This was the biggest market segment that was there. And if you wanted to have a higher range, you had to go to a Tesla or something. You had to pay like 80,000 euros. And now what we see is this new segment in the market that's coming up. Affordable cars, 30 to 40,000 euros with longer range, 300, 400 kilometers. And it's generally accepted that 300 kilometers is a kind of a tipping point that customers would be willing to buy an electric car that would indeed mitigate range anxiety at that moment. And there are different models coming up, the Renault, the Opel, but also the Chevy Bolt and the Hyundai Ioniq. So there is changes in the market. By the way, this is just, if you want to know how sales of cars are evolving and how infrastructure is evolving in Europe, I invite you to go to the website of the European Alternative Fuel Observatory. There you can find all the statistics of all European countries on this thing. Right. Okay. So purchase cost at the moment is still a little bit high. But what about total cost of ownership? It's kind of a different figure because purchase is higher, but operational cost may be lower. So if we calculate the total cost of ownership, we not only have to take into account the financial costs, just as purchase price, taxes, depreciation costs, and things like that, but also look at operating cost, especially at fuel cost, because it's half the price to drive an electric car with electricity than using fuel. And then, of course, you have some other costs that you have to take into account, which are not that much different, besides maybe the maintenance. But if you look at it, we did this actually for the Belgian market, you can see the following. For a typical medium-sized car, so Nissan Leaf-like, we made a comparison, the total cost of ownership, between a classical diesel or petrol car and Nissan Leaf and BMW i3, for instance. As you can see, there is a big difference in depreciation costs here between those two and the combustion engine equivalent, because nobody knows what's the resale value of an electric car after 8 years. So, and it's hard to compensate. Here you see the fuel costs, right? They are definitely smaller in here, but it's hard to compensate. So it's still a bit difficult. However, if you look at incentives now in Belgium, well, in part of Belgium, north part of Belgium, the government is starting to give, started this year actually to give incentives, and you can see that actually at that moment, the total cost of ownership becomes comparable to the other ones. And even more, if Nissan itself, for instance, gives themselves also an incentive, it becomes really, really comparable. So if manufacturers and authorities work together, they can make it, the same price, so that you can have a market breakthrough at that moment. Another thing in Belgium is that you can, if you are having a car for your company, you can deduct 120% of the taxes. And we can see this in the market for big cars. Here's a comparison of total cost of ownership of big company cars. Here, this is the tax deduction brings that this type of cars is really cheaper even than a classical combustion car. That's why a lot of company owners now drive a Tesla in Belgium. So yeah. Okay. So if electric cars are going through in the market, are penetrating the market, who will be your your early adopter? It's who will be the first to buy such a car? Well, we did a choice-based conjoint analysis survey in Belgium, and that allows you to understand the criteria that somebody uses to make a purchase decision, right? And we did this with 1,600 people in Belgium. And based on the preferences that they have in buying a car, you can actually segment potential customers in 4 different groups, and you can see which one would be the most likable to buy an electric car. So we've split it up in 4 kinds of potential customers. First of all, there's the cost balancer. For him, the purchase price is important, but he also looks at the operational cost afterwards. So he really looks at the total cost of ownership. So he's one of the first potential early adopters of electric cars. Then you have another group, which is like a lot of people are still thinking this way, is somebody that looks only at the purchase price. It's too expensive, I just don't buy it, right? They're probably the laggers in the pickup curve. And then you have another group for which the fueling time is really important, so they don't want to change anything of the habits. They want to go, put fuel, 5 minutes, go on, and they're also behind. They will not buy immediately. Another group that would be interesting to buy an electric car is the guys who are stylish travelers, who look a lot at the brand they have. It's nice and fancy to have electric car. They're also an interesting group for manufacturers to target electric cars. So mostly this group and that group are young, educated people with some money, rather than older people alone. So yeah, this is just an overview. I will skip this because we're running out of time. Okay, last point: charging infrastructure. It is important to deploy the right enough charging infrastructure on the right place. Now, where should we put this charging infrastructure? Well, for that, let's see what a car does during the day. Here you see 7 days of a week, and you see the activities of the car. Well, the first thing you can see, most of the time the car is not driving. Hardly 10% the car is moving. Mostly it's standing still. First conclusion is we can probably use cars for balancing of grid and things like that. Second, what we see is that most of it, the car is at home, most of the time. In the week, of course, it's at work as well. And then in the weekend there is some shopping. But like most of the time, your car is either at home or at your working place. So logically, first places to put charging infrastructure is at your job or at your home. Now, this might be an issue. Here you see another city that you may know. People do not always have a garage, right? This is something that we did for Belgium. We have 3 regions in Belgium. The north is called Flanders, the south is called Wallonia, and in the middle we have Brussels, right? Well, in those 2 areas, 50% of people do have a garage and can easily install a charger at home. In Brussels, it's an issue. Only 10% has a garage. So there, they will need to rely on a charging infrastructure which is on the street. Coming to that, we did a study based on GIS, Geographical Information System, for Brussels, on where to put charging infrastructure. And there you use data like see where possible early adopters can live, where there are no garages, where it's densely populated, where there are electricity lines and things like that. And if you combine those parameters, you can actually pinpoint places in the city where you should add charging infrastructure. Right. This was for slow charging, to normal overnight charging, let's say. For fast charging, it's a bit different. Fast charging is rather focused to go from one urban area to another. We did a study for Belgium for that to see where are the best. Well, we have like now 100 charging points in Belgium, and we did a study which are the best areas with respect to accessibility of fast charging. And you can see that the green area is the best accessible. It's like the area between the main cities, Brussels and Antwerp. But these blue dots explain where the biggest communities of electric vehicles are. And for instance, what we recommend to our government then is that here, for instance, there are some big communities and there is no charging infrastructure. So we use this planning to develop and to deploy fast charging stations in Belgium as well. And then finally, the next step will hopefully be some inductive charging lanes that go from one city to another, but that's far future, I'm afraid. Okay, so once again, a key issue in developing electric vehicles is total cost of ownership, minimal attempt, and so Omar will speak about that in his talk.
Yes, thank you, Thierry. It's my turn. I think Thierry took some time rather than we expected, okay? Thierry mentioned that the TCO is really a key issue, but we look behind the TCO. What is the correct design for the drive system or electric vehicles? So I will go to share with you my presentation is I give a small introduction to powertrain technology, our topology and modeling approach, co-design framework, and then I give a small case study for what we did in Brussels. And then I make some conclusion and future trend. So I go for the trend. What's the type of technology now? We talk about electric vehicle, hybrid, and we can look at our screen now that we have hybrid electric vehicle can be classified to series hybrid electric vehicle, parallel, pre-transmission, post-transmission, and also from front and rear connection via road. And then you have combined, one is called complex series parallel, and you have plug-in hybrid. And for electrical, we call it all electric vehicle that we could have battery based, like Thierry mentioned, electric vehicle, and we have also fuel cell battery. So fuel cell vehicle, we could also classify them that fuel cell battery, fuel cell supercapacitor, and also fuel cell battery. So as you can see here, this is an example for series hybrid. I don't know, the pointer doesn't work. So the engine, and then you have the generator, and you have rectification, and then you have inverter to electrify this, transfer the electricity from DC to AC, and then the induction motor. And of course, to improve the performance of the engine, we have battery to be integrated. And in this case, we can improve the performance of the vehicle. Second one is parallel. So instead of you make electric coupling, you have mechanical coupling between the electric axle and engine axle. And the same, we have battery also to improve the performance of the vehicle. And then we have combined system. As you can see here, we have planetary gearbox, you have the mechanical connection with the engine, with the tank, and then you have the battery, two ways that you could charge it from the engine itself, or you can also use it for traction. So you have different modes, and of course the system would be more complex. So you need to have energy management that you could manage these parts. As you can see here, how we can improve this hybridization. So you can start for conventional vehicle. Of course, the conventional vehicle, the engine has a low energy efficiency. And if you go back to electric diesel, it means series based on diesel, you can improve slightly the efficiency. And then you can go for hybrid, fully hybrid, and now we can reach around 41% or 42% efficiency. So there is a need for hybrid system. So you need to integrate battery in the system. And how we can do that? Why? So my answer is to improve the fuel consumption. That's one answer. And of course, to increase or improve the energy efficiency. And then you can make more degree of freedom to control the system. And after that, of course, you can gain also in the TCO. Of course, that also we gain also again in emissions. Like Thierry mentioned, there's a huge impact on the emissions, so we need to tackle this issue for climate change. And this is why compared to conventional system. And if you look for battery system, how we are going to do battery system design, drivetrain. As you can see here, we have battery, you have different battery type, high energy, high power. And of course, if you use high energy, you need to assist the battery during acceleration. So you need to add a supercapacitor system. As you can see in the left side that we have battery is the main traction system, and you have supercapacitor that could assist the battery bi-direction during the charging also and during the acceleration. And then we have another type of configuration. So we have a lot of configuration that you make more flexibility due to the integration. So we need also advanced converter. So you have multiple DC-DC converter, and then we have supercapacitor. You have more freedom to control the energy coming from the battery and supercapacitor. And then we have other advanced technology that you use. One common DC-DC converter that you integrate the battery and supercapacitor. We use common thermal management, common or centralized control, as you can see here. And then you can control that battery is wrong here. So you can use supercapacitor with high energy battery, and then you can integrate high power with high energy. So we have more flexibility that you can control multiple sources to satisfy the need of the vehicle. So, and then you have advances of this hybridization electric, so we can improve the battery lifetime. This is a key issue. So we need to improve the lifetime of the battery. And of course, this will lead us to increase the efficiency, because if you improve the energy content of the battery, it means that you gain also in the range of the battery. So, and then you can also include inside the DC-DC converter advanced technology like wide band gap technology, like SiC technology, GaN technology, and now we can gain more in efficiency. Once you gain in efficiency, you can also improve the energy efficiency of the whole drive system. And of course, this more flexibility and also more reliability. So how we can go for fuel cell? Thierry mentioned that about electric vehicle, but there's also fuel cell vehicles. So what is the challenge there? So as you look at the fuel cell, low dynamics, low dynamic, and also high cost, high size, and no capability to recuperate energy from regenerated brake during the driver. So there is a need again hybridization. So we need to hybridize this fuel cell with battery or supercapacitor. As you can see here is the first trend of fuel cell integrated with supercapacitor. We can gain in this traction system, or we can integrate fuel cell with battery with the same content of the drive system, or we can merge the three sources. Of course, it will give more freedom, but also more complexity in the control system. And this is why we can gain in this drive system with multi-board. We can use advanced technology like interleaved DC-DC converter that could manage the energy transfer between the sources and the traction motor. So I'm going to share with you the modeling, how we are going to design the drive system, how we are going to make modeling that can fit our design and also deliver the need of the user. So we need to highlight that there is a need of user that you can achieve TCO minimization, and also energy management or energy efficiency should be higher. So I'm going to see how we can do this. This is a classification of the model. So we look for the model that you could achieve transient. So you consider the transient consideration, a steady state of the vehicle, or dynamic, or quasi-static. And then model representation is structure or functional, or the calculation of the model should be forward, backward, or backward, forward. This is the idea how we can make the modeling of the drive system as well. And then you go for causality, and then you causal or not causal, and then we can go for actual design for the vehicle. So I'm going to see how we can make the modeling approach. There are three main approaches. It's called forward approach. Does it mean that forward you get from the battery? This is the direction of the power flow. You have the positive power go to the wheel, but the calculation in this case coming from the dynamic, means that the environment, from the wheel itself, you get the dynamic of the vehicle, you calculate the efficiency map of the motor and driver and DC converter, and then you size the battery. And this is basically on given drive cycle. You have the drive cycle, and then you make this modeling approach. Second one is we go for positive power flow, but the calculation is coming off from battery. So we have the battery, and then you have the DC converter, motor, and drive or inverter and motor, and then the dynamic of the vehicle. And this, of course, based on the driver itself. So the driver itself, you give a signal. I need to deliver this torque to the wheel, and then, of course, the battery should respond to this needs. And this is what we call it forward approach. The third one is called, I think is one is missed. Okay. And then this based on the model that you use. Low fidelity model is like efficiency map, or medium fidelity model, or high fidelity model. This is go for complex or a small trend of the model itself. As you can see here, low fidelity model, we talk about half second, 1 second for the modeling itself. So you can make the block set of each component integrated together, and then we give the execution time is half second, 1 second sampling time. As you can see here, if you are going to make the small block for the motor and the inverter, we can take the efficiency map based on torque speed. As you can see here, the torque, the efficiency or the torque map of the motor is constant torque, constant power, and then you can, based on the setting point, you get the efficiency that required on this operating point. And then this is why we need to consider efficiency map is really detailed one, and also there is no transient. But if you go for complex modeling, so you have really detailed model for each component, like motor. So if you are going to make modeling of the motor, you go for DQ model. which means that you transfer the motor to be in DQ modeling, and then you also design the control. And if you design the control, you have to respect the control bandwidth for the acceleration and deceleration for the motor. It means that you are going to do sampling time lower than millisecond. And of course, this will take time to make the modeling of the system. And of course, that we need more dynamic models. Transient already considered, so you can see the transient of the machine itself or the transient of the switching of the inverter and so on. And this is why we call it high fidelity models. Of course, we have the model, we know how we can make the modeling integration and so on, but there is a need to make the control itself. So how we are going to make the controls, there are a lot of control techniques that based on rule-based or optimization-based or learning process. So we have different categories. If you can look at this, so we have role-based also could be divided to the deterministic or fuzzy control, and below these categories we have different controls that could be used. And if you go for optimization techniques, we have online and offline, and of course for reality we have online to emulate or simulate the real drive vehicle. But of course, the engineering would like to have also offline to make the optimization for the drive system. So we have also category of optimization techniques that could be used for optimizing the design or also control. And then we have learning-based. So learning-based that you also make some neural networks that you have real data, you train your system, and then you let system work for real demand or real inputs. And this we call learn-based. And this means that you could be step forward for automated car. So you have automated car that you have to be driveless. So it means that you have to make the learning process for this car, and then you go out for the driving, actual driving. So this is the driving system. Okay, so what we have to do is how we are going to make representation for the forward calculation or backward calculation. As you can see here, we can start for forward calculation. We give the driver gives the speed that he needs, the energy management that we also explained that he gives the set point for the torque that required from electric part, and the set point for the mechanical part. And then we have this forward calculation for the drive system. Then we have backwards. Backward, you have the drive cycle is well known, so you know the drive cycle. We add the drive cycle to the vehicle dynamics. We calculate the torque, and from the torque, from the power need and torque need from the wheels, we have the energy management that also make the differential between the torque required from the battery and torque required from the engine. And in this case, we calculate the energy consumption. And then we have the representation for the same forward calculation. You can see here we make the input-output interface during the modeling. So we have the model of the battery, the DC converter, the motor, and so on, transmission. And then you have detailed control algorithm that you have the measurement, you have the state of health of the battery, state of charge, and then you get the splitting between the two sources. And again, for another approach that we combine forward calculation, backward calculation, as you can see here that I mentioned the drive cycle, and then the drive system, electric drive system, you have the energy management, and then you go back again to ensure that what you ask it already delivered. I'm going fast because the timing, I guess, is very short. We did some analysis for the impact of the energy management on the vehicle itself. As you can see, if you have series hybrid with supercapacitor with the engine, and you can see here that the distribution of the power. So we have the drive cycle, how we are going to make the distribution between the engine and battery. So we make use of on-off control. So means that if you have high torque, the engine should deliver torque. If you have less torque, the battery should deliver the power, as you can see here, or the supercapacitor. So this is the trend of the state of charge of the supercapacitor. And what we gain here, that if we change the control strategy, we could gain on the energy saving. So you have here the energy, the size and the energy saving. If you put this energy with this amount of the energy sources, I mean the electric energy source like battery or supercapacitor, you gain in energy saving around 30%. If you increase it, you will have also 35, but another energy management could be used to minimize the system. I'm going fast for this, the co-design. I know this too fast. So actually, the co-design, I mean, you start with the topology, like I mentioned before, and then you select the sizing of the battery and supercapacitor and so on, and then you optimize the control. And this is how we can make the optimization of the drive system. So what we could do is, how we can do it is called sequential approach, or nested approach, or iterative approach, or simultaneous one, that we could have the trade-off between the sizing of the component and also the enlargement, and get the trade-off between both of them. So I'm not going for detail on this, but due to time. So I'm going for case study what we did in Brussels. So in Brussels we have a huge demand on the electrification in city, but here is buses, not passenger car. What we have is we have a standard 12-meter buses, and we have 3 lines. 2 lines is 12-meter, and the third one is 18-meter buses. How we are going to use our knowledge, our co-design, that we can make the electrification in city in good way, and also how we can make the location of the charger in cities. So what we did already, we have this standard, based on the requirement of the city. They mentioned that the line 86 and line 17 is standard, is overnight charger. There is no on-road charger. And 18-meter is on-road charger. And we can implement 450 kilowatt. And in this case, we look for the specification, which type of battery, what the energy content, what the voltage of the battery, and also charging power, charging time, and so on. This is a look characteristic. We get the measurement from the city, and based on the measurement, we designed the electric bus. So what we got, we use our co-design iterative approach, and we get this basic system like we did before, battery, and then inverter, motor, and then we make the energy management. And once we get the line 86, we calculate the back force energy content, and you can see here that power delivered from the wheel, so the blue one, the red one, and the blue one is the power required from the battery. So we design the battery, the system, and we get the battery power and the energy. And this is go and back, but they would like to have 12-hour autonomy. It means that the bus should work without any disturbance for 12 hours. And as you can see, we use based on the code design, we got LFP 40 ampere hour, and the energy content of this bus is 1.8 kilowatt hour per kilometer. And the depth of charge, I mean the range of the battery that it changed from the self charge 100 to 10 is mean DOD around 90% operation. As you can see here, this is trend of the state of charge of the battery and the voltage of the battery. And we come out with the design of the charger. If you are going to use this standard buses, we have 40 kilowatts should be implemented at the depot. And we need to charge the buses with 4 hours and 15 minutes. As you can see here, the trend of NMC, if you are going to use NMC battery with 20 ampere hour or LB 45. I'm going the same. This is the same trend for calculation. We use another line. We give the code design, how we can make the design, and then you give us this calculation. So we get for line 17, we have energy content of 1.3, and the charger power is 60 kilowatt, and the charging time 4.5 minutes. And of course, this will be based on the NMC. And then, yeah. 5 minutes? Okay, perfect. So, okay. Yes, okay. So, and again with the heavy duty line is 18 meter. We did the same. We use the code design that how we can make which battery type and also which battery voltage that could be used. The code design gives LTO is the best selection for on-road charger because this one will be on-road charger. So you install the charging on-road at the terminal. So we have this back force calculation, and then we have this integration of the charger. So how can manage the charger itself? So we can charge the battery with 200 volt, 200 kilowatt, and then again you go to charge within the stop, and then back again you drive, and then you charge, and so on. This is the trend of this for this bus, and you can charge time is 7 minutes, and the power needed 200 kilowatt. And this is how we implemented the charger at the end, at the starting point. So this is a summary of what we have. For 2 lines, the standard one, we have overnight charger with 40, 60, and for online charger 200, and this is the trend of the charging point. Of course, there is a need to integrate with a real-time or real DC sources, and now we have conclusion. So the co-design is really enable our tool for designing drive system. Of course, the auxiliary of the electric bus has impact on the energy consumption, and then LTO is the best selection for the electric bus on-road charging system. And this is a trend of future work that you could integrate the charging to the existing DC network, and also you can use the capability of V2G to make load shaving of the system, and then you can integrate up to 600 kilowatt on-road charger. And this is my fast presentation. Thank you. And this, if you need to follow us, this is the main 3 project that you could follow us on it: mobility for EU and elliptic and Orca. Thank you.
Thank you very much. I'd like to invite Professor Coosemans to the stage as well to answer any questions that you may have.
I think we sit here, no?
Anyone got any questions about powertrains and? No? I'd like to ask the bus example that you gave us, that's operational in Brussels today, up and running today, is it?
Not yet.
Oh, okay.
What we have, actually, we had the measurement of existing standard diesel bus, and Brussels City asked us to design the future electric buses.
Okay.
What we did, we make the study, we give the correct design of the electric bus, and they make a tender for the new electric buses. So I guess by next year we have around 25 electric buses will be running in Brussels, from 12 meter up to 10 meter buses.
Okay. And have you been able to quantify how much energy that will save the city, or what benefits it will bring to the city?
Should be aligned with the whole strategy, because we only electrified only 3 lines, but we gain a lot in the emissions, because if you compare diesel bus and the electric bus, we gain a lot, around 40% of the reduction of the energy contents of the bus required. So it means that we gain a lot in CO2 emissions.
Okay.
And of course the cost as well.
Right. Okay. Thank you.
Yeah.
So, if no one has any more questions, I'd like to thank Professor Hegazy and Professor